Okay, we're live. We've got Rohit and Tara again.
Hello.
Hello.
Oh.
Let me just.
Hello.
Let me just. Who's? Let me just. This. Who's? That was probably me.
What? What's going on?
Oh, you didn't hear because you're not on the listening to audio on the stream. There was a loop, and I was like, "Who's not on headphones?" But it was me. Let's see here. All right, we'll get started in a minute. I just need to. Notify a couple of channels. Okay. Oh, also quick little thing. I got a email from my apartment office or whatever that there's going to be a testing of the fire alarm system basically between now and the end of the stream. So at some point we might have to pause while I mute it so that we don't have to listen to whatever the fire alarm sounds like here. I haven't heard it yet.
Cool.
The worst.
Yeah. And let's see. I think we're about ready to go and on time at 11.
So punctual.
I try. Trying to remember if there's anything else. Okay, no, let's go. Let's go. All right, you can see I was just looking at where Rohit had a little to do, which we did a quick little review. It doesn't look like it's ready yet, so I'll just leave that here. But so yeah, Wanix, for people that are new, Wanix is let's see, do I have a browser open that I can use for the stream? What's this one? Yeah, maybe we can use this. So about a year ago, built Wanix, which is a kind of experimental Unix-like development environment that is entirely kind of WebAssembly native. And you can watch this demo. It's really proof of concept, and we demoed a lot of cool stuff, but I was a little unhappy that one of the core inspirations for it was Plan 9, and we didn't have some of the core magic ideas from Plan 9. And so this month we're kind of basically starting over from scratch and building Wanix, a new version of Wanix 03. And so far we've been kind of putting together the abstractions that we're going to use, kind of the toolkit to build Plan 9. And a lot of that has to do with file system stuff. So the last couple of streams have been about putting that together. And today, let's see, what do we got today? Hopefully today we'll actually get to building kind of the first specialized file system that's a very Plan 9 kind of file system, which is, and I'm going to call these devices because file system sounds like data storage, but Plan 9 used the file system as an abstraction to basically control a lot of the whole system. So, for example, this little file system device that we're going to make, the first one is a device to control other devices or other file systems. And again, device and file system is going to be used kind of interchangeably here. In Wanix, a Wanix device is a file system. Just like in Plan 9, pretty much every component of Plan 9 was they would usually call it a file server. And they have the 9P protocol, which we'll get into a bunch of cool stuff there. So let's see what we have so far in this code base, which you can kind of follow along in on GitHub. It's in a new branch, 03. So if you wanted to try out what's in the demo and stuff, that's in main still. And then 03 is where we're kind of doing this active work where we pretty much started over. And we've got just to kind of get started, we stubbed out a little command line tool with one command, which is serve right now. And we basically were using this to get to a point where we can kind of try out our file system abstractions. For example, we've been making this in-memory file system, which lets you define a kind of basically a virtual file system as a map, very much like a Go map. And then we have a package called fskit, which lets us take a file system and mount it on our actual system. So it'd mount it temp Wanix. And then that way we can interact with this using our shell and whatever else. It's an actual part of our file system. And let's see, where I remember what we got to on the last stream was we got this working. Let's try and get this working, and we'll go build command Wanix, and then we have the Wanix command, and if we do serve, and we're going to get a bunch of debug stuff. But now there is a Wanix directory. You can see there's a hello file with hello world, and then a couple of directories, then with a file ken. The problem was, I guess, where we ended last time was kind of realizing that this in-memory file system is a read-write file system. We should be able to modify these files and create new files and stuff like that. And it turns out the code that I wrote for fskit only supported read operations, so we'd only be able to do what we've done so far. And so since the last stream, I've gone in and updated fskit to handle writes, and it's still missing some stuff. I don't believe we can make a directory in here. Nope. But we should be able to new file contents is write to these files. New file contents. Oh, that's an interesting bug in that it didn't actually truncate it like it should have here. So I'm going to mark this fskit not truncating when writing to a file. Hopefully, I mean, we might have to fix that in this stream, but I'll kind of put it off. And in theory, we should be able to make other files, so we can create a file. Oh, not support. Oh, that means it crashed. Nope. Create operation not supported. Well, we're getting there. But at least we can do some basic writes to it. Luckily, most of what we're doing doesn't involve writes, so we can kind of put that off. This is mostly a kind of a read-only file system. The way this works, let's see, and then we would have like a memfs. So, oh yeah, thanks. But there's not that. So in plan this, so as a plan 9 pattern, a way you would create a resource in the system is there would be a file called usually called clone. We're calling it new here. And when you read that file, that sort of allocates a new resource for whatever it is. Common example in Plan 9 was actually TCP sockets. So you could create TCP sockets through the file system. And so this is a pattern that you can kind of apply to anything. And so here we're using it to create new file systems in our file system that we can then mount in different places. So we'd read new, and the contents of that would be a number that represents the ID that is used as a directory for that new resource. And then you can use that to go into this directory, and there'd be a couple of files in here. You know, name and type are basically properties of this file system. Mount would be the actual file system itself. So if we created a new memfs, presumably it's empty. And so we'd have mount would just be an empty directory. And then we could use bind to put that wherever we want. So we could create a new directory like, you know, data. And then it's powered by this file system, which is an in-memory file system. And then as we go on, we're creating new types of file systems or new types of devices. But the first device that we have to create is this one that lets us manage these file systems or devices. These control nodes are basically how you would do commands. So instead of having commands or even syscalls, a lot of stuff in Plan 9 was done through files that you would write to. So you'd open up control, and then you would write to it almost like a command. You know, you give it had arguments and stuff like that. And then when you close, it would perform that operation. And so kind of the benefit is we're doing all of this stuff, and the whole system is only using the file system API. And because the file system API is universal, you know, every operating system now has the file semantics API for this kind of file system stuff. We can kind of embed and make this Wanix system controllable in any of these environments. There are a lot of other implications of this long term. But anyway, so that's just kind of setting up and what our goal is. But one of the things that I've done since the last stream is put together a new package to help us build these. So we'll go into the file system abstraction that we originally set up. But when building these kinds of little file systems, these little devices, you can kind of break them down into like subcomponents, right? If we wanted to, every time we create a new file system, it's going to create a new directory with these files. So can we make that as sort of a mini file system or a mini device that we can instantiate every time we call new? And then this listing, all these directories that map to those little subfile systems, that's another pattern. And then defining these sort of non-numeric files that are very specialized in what they are, like control is sort of a control node, and new is for instantiating new things. We kind of want to have some tools to build that up easily. So as a refresher, we've extended the Go IOFS package, which gives us a more extensive version of the file system API that actually covers most of the things that you would do: make directories, create files, remove files, rename files. And so implementing a file system is sort of the way this is set up, Go IOFS. The minimal interface that we have to implement for a file system is IOFS, file system interface, which is open. So we just need to implement something that has an open method, and then that has to return a file, and a file has to at least implement stat, read, and close. Again, as a minimum. You could also implement read at, write, other IO related methods. And then stat has to return a file info thing, which is all these methods. So even though it's relatively simple to implement a file system in terms of you just need that one method, you actually need to implement all of these methods. So in the previous sort of iteration of this abstraction, where we then created a bunch of types of file system implementations, like here's a GitHub file system that would, given a GitHub credentials, it would actually use the GitHub API to let you directly manipulate a repository on GitHub, and you could then mount this as a file system and work with the file system and have it behind the scenes actually be updating a repository on GitHub. But any of these file systems that we make have to implement a lot of stuff. I'm trying to find a good example. Well, so besides previously, you'd have to implement all of the methods that could be implemented on a file system: chmod, chown, chime, create. And if you're doing a read-only file system or something that doesn't support them, you'd have to return error unsupported. Our new FS package, because we broke those into separate interfaces, we don't have to implement those. It'll just automatically return unsupported. But we still have to implement open, and which means we still have to implement a file. So where's the file? And so a file is going to have read, might have write, might have sync, seek, close. If it's a directory, it would have read dir. And then, of course, file info, which is the metadata about it. And so pretty much every time we implement a file system, we re-implement file info, which a lot of the time is just a struct, and then these methods are going to return more or less those struct fields. There's a kind of an interesting pattern where there's another interface that comes up when does it come up? I guess when you do a read directory. So when you're let's see, is it one of these? Yeah, if you do a read directory, you don't get stat objects, metadata that you could use to see, here's a listing of files in a directory. You get a dir entry, which is another interface, which is very similar to file info. We have name is dir. We have type, which actually returns the file mode. This is very similar to name mode, kind of a type, is dir. So I'm not exactly sure why they ended up doing this, but it's interesting that it's basically the same info. So a lot of the time when implementing these file systems, we can create a struct for file info and implement the file info stuff, name, size, mode, mod time, is dir, sys. And then we can also implement what this interface has that stat doesn't, like type, and then info, which then gets the rest of the file info. And so by implementing those on the same struct, we can use this struct for both anytime we need to return a file info and anytime we need to return directory entry. So that's handy. We also need to, of course, like for any file system, also return a file that has these IO things. And the architecture of this is so similar. Like a lot of the time, it's either delegating the read and writes to some other thing that you can read and write, or we've read all of the data into a slice of bytes, and then we're going to read and write against those slice of bytes. And we do this a lot. Like I'm trying to think of some other, let's see, makefs. This was an experimental file system that would let you almost like building make into the file system. But anyway, so we implement a file system and then file fs file. Let's see. I guess we didn't need to implement something, but in our memfs again, we implement file system stuff. Because our memfs was based on the Go fs test, there's a test package that has a file system implementation called mapfs, and it's an in-memory file system. It's made for working with tests, and because of that, it's read-only, and we want a read-write version. So our version, that's why we created a separate version, but we sort of took the basic implementation of this because it did something that was kind of convenient in that you can define a map like this where the file data is all we have to specify, and any parent directories it will automatically create or synthesize. So that way we don't have to create, entry for fortune and then create an entry for fortune K, and then we can create this. So that was kind of a nice convenience feature of this implementation of a file system. And because it's a type derived from a map, we can do this kind of map style declaration where we can just kind of declare it and then do these key value things like as if it were a map. So we took that implementation and expanded on it to create a version that we could also write to. and also create new directories, chmod, basically implementing more or less a full file system. There's a lot of code here. I'm going to make this a little bit smaller, and hopefully this is big enough for seeing on the stream. What do you guys think? Is this still readable?
For me,
It is
yeah.
readable.
Yes, from Tara. Rohit?
Yeah, it is pretty readable.
Okay, cool. And then here again, we can see we're implementing a file info. In this case, they did an interesting thing where they kind of built up these nested structures where here's another tricky thing about this. In order to be able to declare these, the file data in this way, where we can just kind of, this is kind of a rare syntax shortcut, but normally writing Go, you would have to declare a struct like this, map file. But because this is a map structure where the value type is declared, Go does infer the type, and so you can just open a bracket. A few times that there's some nice kind of type inference that lets us type a little less. But anyway, because this is a struct type, we can just define these fields. There's a data field, there's a mode field, so we can set file permissions. If we wanted to set the last modified time, we could. And we can just set those as fields. But the problem is, this type can't be our file info, because file info has methods with those exact same names. And because those are exported, meaning we can, they're public fields, and so we can set them, we can't have both. We can't have a mode field and a mode method. So they wrap it. They say, here's a new type called map file info, and it has a field, a private field of a map file. And then for most of these things, it's just accessing that struct. And for some reason, they put name on this. So whenever they need a file info object, they'll set that up, where they're like map file info, and then have a map file in it. Let's see, where's an example of that? So here's a map file, and so it creates a map file info. And then when it needs to create a file, it then there's this other type. Anyway, I kind of like that this is a sort of composable nesting thing, but it's a little confusing. And the other problem is that a lot of what it's doing is not specific to this type of file system. Here's another example where, in order to create a file that represents a directory, you implement a file that implements stat, close, and read, but then also you implement readdir that returns directory entries. But these directory entries are basically just, it's looping over a field that contains, in this case, map file info, which implements the dir entry interface. So there's kind of a reusable pattern in here, and in implementing a lot of these file systems, and we're going to implement a bunch, we need to kind of easily create these like files and file info and dir entries and all of this. So since the last stream, I put together this package called fskit, which is mostly centered around this type, which is technically named n, but we'll refer to it as node. The reason why we did this is because we'll mostly be defining these nodes with this function, but you can't have a function and a type with the same name. And since we're otherwise not really typing n or using the n type, we can just use this abbreviation. It's almost internal. We could have made this unexported by lowercasing it, but whenever we return a type from a function that you can call, I like to have it an exported type so it shows up in documentation. You can return an unexported type, but there won't be docs for it, and so you're just kind of confused. So anyway, this is sort of a generic thing that implements file info, directory entry, and can be used as a file. And we can sort of define as much or as little as we need for a particular use case. For example, if we're making directory entries to return from read dir to get a listing of directory entries, we don't need file contents and we don't need all of file info, so we can easily just specify what we need for a dir entry, which is, I think, just name and type from mode. And there's also kind of a clever thing going on here where because we're trying to create a type that implements these interfaces, we can't do what they did here with map file, where you can just declare a struct that has the data that we want to have. Where, if we're creating a little virtual file system and we want to create, the data for a particular file, we can't do that because all the fields for the struct have to be unexported so that we can have methods with those names. So this is kind of an interesting Go-ism, but we kind of rely on this node kind of constructor to build these. And instead of having a defined function signature where we always provide a name and we always provide data, because we won't always be providing data, or sometimes we'll provide just data and not a name, or maybe it's just name and mode but not data. We need a really flexible kind of way to define these. And because Go, some languages, C#, I'm sure, Rohit, you're familiar with actually I don't remember the specific term, but when a method can have multiple signature types.
Yeah.
I forget the name of that too. Doesn't matter. Yeah. Most languages don't support that. Go doesn't support that because it is kind of, extraneous. And if you think about it, makes APIs way more complicated because now you can call the same method a bunch of different ways. That said, to do something kind of like that here, there's a pattern in Go where you can use variadic functions, which are functions that take sort of a final argument, at least in its declaration, that represents 0 or more arguments. And so in this case, we could call entry with name and mode, and we could just call it with a name and a mode and close it because variadic arguments are totally optional. But then if we wanted, we could add more fields if we wanted. and they'll just show up as values in more or whatever our variadic argument is. And so node is actually just a variadic argument, and its type is any, which means it can be any type. And this kind of works because all the things that we could specify in here are different types. Like the name of the file is always a string. The data is always a slice of bytes. Size. Sometimes if you're doing a directory listing, you want to have size information, but you don't actually want to have the data. So anyway, all of these are kind of different types. And so what we can do is take arbitrary, we'll call them attributes, loop over them, and then do a switch on the type. So we can be like, oh, is it an int? Then we'll set size. If it's a time, we'll set mod time, slice of bytes. We can't do this for, this is kind of a funny thing that we can really only do with this type because they all have different types. But conveniently they do, so we can do something like this. I added an extra thing that says if we have a file info, it'll actually copy all that in there, so we can kind of use that as a shortcut sometimes. So anyway, now we have this sort of generic way to declare, we'll call this a node, and maybe sometimes it has a name and a size, or maybe it's just data, or maybe it's just name and data. Very flexible. And then it implements file info, directory entry, as well as file. So assuming that we have data in here, it also works as a file. So you can see here, it's implementing all these methods to satisfy that interface. Size is kind of interesting. If we didn't set size, but there is data, then it'll use the size of the data. But if there was no data, but there is a size, it'll return size. And actually, technically, it doesn't implement file, but it does implement fs, which is kind of funny. Which means it implements open, and open gives us a file. So you can also think of n as a file, it represents a file conceptually, and it implements a file system that you can pretty much only open dot, which means the current directory or the root of this file system. And then it gives us a node file. Part of the reason for this is because file is stateful. Every time you open up a file, it has a little cursor or an offset, because whenever you do a read, it updates that offset so that it'll read the next bit of data. So this ends up working really well for that. And then just have this weird property that these are also now file systems. And it actually kind of shows you how we can kind of use file system to model anything here. A file system could be, a whole file system, of files, whether it's, a read-write file system or, a read-only file system with predefined stuff. Or it could be a file system that has one file that is just a file. It's not even a directory. And we use this as a way to unify some tooling. I'll show you in a bit. Let's see, node file also implements, let's see, it doesn't implement a directory, but we have another helper here, a directory file. that just needs a file info, which could be an N, and then takes dir entries, which could also be an N type. And it's just a generic directory file, because a directory is always a directory. It's basically a thing that you can't read. You can get metadata about it. It might have a name, size, mode that says it's a directory. But mostly it wants to have this read dir that will give you a listing of directory entries. And that's always the same. Like, a directory always works the same. Read dir is weird in that it also works like read in that it's stateful. You can call read dir with -1 and it returns all of the directory entries. But I guess because for efficiency, or like really large directories, they designed it so that you could kind of say, give me the first 10 directories, and it'll give you the first 10. And then you can say, okay, now give me the next 10 and the next 10, or whatever number. So you can kind of stream out the directories. And again, that requires an offset. And so a directory is stateful in that way. But then this lets us create a generic dir file function that will give us a file that is a directory. And we just need to give it a name, a mode, and then entries, which are the directory entries that it's going to return, which can be defined with N, our node. So there's no tests for this, but for some examples, does that kind of make sense? There's a lot going on here. But basically we have a generic way to define file info and stuff like that. As an example, we'll be able to get rid of all of this code because we have a generic version that we can use for this file system. And we don't have tests for this, but it's probably time to actually start writing some code. There's some other things in here that we'll kind of get to as we get in here. So yeah, and then there's open func. So basically just utilities for building these kind of virtual file systems. So we started this in-memory file system, and really the point is it's like a read-write, a generic file system that you can write files into and read them out, and they're basically stored in memory as byte slices. It turns out that that's such like, if you're building any kind of file system, when we look at this guy here, we're going to build, this file system, and each of these files is going to return something. And so we have to create, a file for each of these that's going to basically be in memory because it's dynamic. So we read the data, put it into sort of a in-memory file, and return that when we open this file path. So it turns out a memfs isn't just a useful, sort of virtual file system, but it's kind of what we need to build a lot of other file systems. We need the primitives of creating a virtual file and a virtual directory, and then we can kind of compose these to show you what I mean. As a sketch of implementing this, I did a prototype for another type of file system we'll make for managing the processes in this sort of operating system. And it looks very similar. Basically, it's going to have a new with subdirectories for every type of process you can create. And then there's going to be a directory for every process. And, every process is going to have, some properties and different, they'll have its own file system. So I wanted to sketch this out to see how, what's like a really concise way to describe a file system like this. So this is kind of a sketch version, but basically it's read-only, so we don't have to implement anything other than open, which we still need. This wasn't really meant to actually be used, but just to context background. Not open context, but open. So there, now it implements the file system interface. So now device is a file system. And we've got a field called resources, which is a map of a string to a file system. And this is basically in this case, these would be processes. And to register the different types of processes that you could create, there's a mapping of kinds. So I don't know that this would actually be accurate, but it would a mapping of the name for the kind of process that it is, whether it's native or whatever. And then a factory function that will return, here's a new instance of that we could then put into resources. This should probably return a file system. Again, this was just kind of sketching it out as a way to sort of see what needs to be implemented to build something like this. And then we get into actually implementing the file system. And this is pretty much like, there's not a lot of code here, but this is enough to implement a file system that operates a lot like this one, where we have new, we don't have control, but we have something else called self, that in the case of processes would return the ID of the calling process. And then a bunch of numeric directories with their own little kind of files inside. So this was done by sort of combining a bunch of things. First of all, our resources are already in a map to file system. So, we'd have 1, 2, 3, and then whatever the file system or directory that those would have. We're basically storing those as a field. And so we just need a way to turn this into a file system where there's a directory for every key in this map that there's a directory for. And so that's what mapfs is. So by doing this, that turns our resources field into a little file system or directory where every number is a directory. And then we also have these two other files nodes that are in the same directory as those. So we use mapfs again to declare these two names. And then each of these has to be a file system. And to quickly declare a file system as a closure, there's this open func utility. In HTTP, when defining HTTP handlers, it's all path-based. It's very similar to kind of what we're doing in file systems. But normally, to implement a handler, basically a unit of HTTP that could be at any path, you implement a type with serve HTTP. And then this is your, where you can look at the request and then figure out how you want to write the response, what you're going to write out as the body. So this, because it's a interface, you can create these little kind of modules of handlers. Like, for example, here's a file server where you can just say, here's a directory path or whatever, and I want you to just serve those files over HTTP. So it creates that and returns a handler. And these handlers can then be put at different paths with a kind of a muxer. But something like this. You can do handle and then a path, very similar to our mapfs. But one of the ways to create a handler, sometimes you don't want to create a new type that implements a serve HTTP method. So there's actually a helper function called handle func. Or sorry, is it? No, I think it's handler func. Where is it? Something with func. Handler func. I always hated that. Very similar naming conventions. Anyway, a handler func is basically a type derived from the function signature that is basically the exact same signature as serve HTTP. And all this does is create a value that has a serve HTTP that calls the function. So this is a little Go pattern. You can see it's really simple. Handler func. Here's the function. And then because we can put methods on any type, here's a method for that type, serve HTTP. And all it's doing is calling itself, because it is a function, with those arguments. And so now we have a way to create new handlers with a function or a closure. And we don't have to create a new type or anything. That's basically what I did here. Because ultimately a file system is just something that implements open, it'd be really nice to declare a file system by just implementing a function that looks like open. And because I have this context variation, we do both. But so here we have a open func type. So if we declare a function that looks like this, then we get something that implements file system. So now we can create file systems by just implementing a function that looks like this. So that's how in here, our mapfs new, so that's going to be a path in the file system. And then we use open func to declare a function that will return a file system. And so in here we can say if name is dot, then that's basically what happens if we open new directly. And in this case, we want to return new as a directory that lists all the possible devices types that we can create. So we're going to make a dir file. So we have this helper here, dir file. for its stat, we need to specify the name again. And then we give it a bunch of dir entries, which we can create with fskit node. As a kind of a convenience, I made another sort of way to create nodes called entry, in which case then it's sort of like some of the function signatures defined. We're always going to have a name, we're always going to have a mode, and then we can specify other stuff like we normally do. But this gives us a little bit more structure and kind of semantic meaning. So here we're defining a directory file, and we're basically just making a list with entry. So we loop over our kinds map, and for every key, we want to make a directory entry. So it's a file of 555, which means I think that's read write. I don't remember. But anyway, so now new is defined here. And then if we open up a subpath to new, which should basically be pointing to one of these entries, basically a kind, that's also defined here because that's every other case other than dot. And we look up the kind and we get the factory. I think it actually would look like this if we changed, because factory, yeah, it returns a file system. But it also returns an error, so we would do file system So in the case of opening /new/ whatever, if it exists in kinds, then it will look it up and get the factory that was registered for that kind, call it, and it gives us a file system. And then we use next ID, which is just a counter. We increment it, so it starts out at 0, it becomes 1, and then we put in our resources, convert that integer to a string. So now in resources we have a string of 1 equals the file system that we just instantiated. And then lastly, what happens when you read from a new, it's going to allocate that resource like we did here, and then return a file that has the ID that you can look it up at. So again, we're using entry. So this is why fskit was put together, so that we could pretty easily define these kinds of file systems, because we're going to make a lot of these, and so we don't want to be implementing a lot of the same stuff. We don't want to implement, we don't want to implement all of this stuff, file info and every time we create a file system. That makes sense, right? Sorry, I haven't been pausing for any questions.
Yeah.
I was just trying to really get through this. I realized that I'm doing a lot here, so
It's a big jump from like the old MFS system.
yeah. So
But
we're going to port the MFS system to it, so we can kind of see more how to use some of these primitives. But also really quick here, you can see how we can combine these. So here's one mapfs that we kind of declare inline for self and new. And then for the other numeric directories for the resources, we can also just cast our resources field into a mapfs, But then we need to combine those. And so that's what union fs is it's basically a slice of file systems. So we can just kind of declare it like this, where it's a, here's one file system and then here's another. And what it does is it implements enough of a file system that it can merge them. So they're sort of overlaid. And so the result of union fs is a file system that has self and new as declared from this mapfs, as well as all of the numeric directories from here. And once we have that file system, we basically call fs open on it. So we kind of, this device that we've created is basically dynamically creating a file system and then calling open on it. And so then we have a composed file system, and we can declare it pretty concisely. So we're going to implement something very similar to this for our file systems device. But first, there's a problem. I didn't implement, mapfs does not support sort of looking up subdirectories of a defined map entry, which is exactly what we want with new, because new is a directory and then it's going to have, a bunch of files in it. And this is because, again, I ported this from the fs test package, the mapfs, only I've changed it. Instead of pointing to a map file or something that represents a file, it points to a file system, which we can use to represent a file very easily by creating, by having the file implement open, where open dot returns the file. So we kind of use file system as a very generic, well, it could be a full file system that does something totally different. It could just be a directory, or it could even be a file. But all of those sort of are handled by this type, and we define mapfs around that type. So it makes this very powerful. We don't need another type that, is different for, whether we're composing file systems or directories or files. It turns out the file system interface is flexible enough to represent all of those. So this is a modified version of that mapfs, which what I love is that it synthesizes parent directories. And these tests come directly from the testing mapfs. So you can see it works just like kind of the testing fs version, except instead of specifying map files, we use node. So here's an example where we're defining a file system where the root is a directory with 777, that's read, write, execute. And then here's a file. Notice that node doesn't specify data because for whatever reason, this test doesn't care about data. So, whereas this test does care about data. So node is a very flexible way to define a file like, file related object, which is great. Now the case that we don't have here, test mapfs subdirectories. So we're going to create maybe we'll create so this basically represents a directory, and then we're going to test, and then we're going to create another file system that has just a dir. So in this case, what would you expect there to be in this file system? There's going to be a dir entry, which is a directory, and then
yeah, but there can be other files.
There could be a file, but because it's a file system, it's basically a directory. Because ultimately a file, directory and file, there isn't really a difference other than a directory implements a method that says what files are in it. We basically have composed, we said, here's a file system that has these files in it. So effectively now we'd have dir hello, dir fortune kken. That's what we want. Unfortunately, the current implementation doesn't do this. So let's check this. You can use testfs to check that we have a dir. I mean, we'll check for dir hello. Yeah, well, it gets it. And we'll run it, go test fskit. Oh no. So something. So testfs does a lot of things. Like it's supposed to effectively, check to see that these files exist in the file system that we pass it. But it actually does a bunch of other stuff to make sure that they behave correctly. So it failed for some reason. Let's find out what's going on here. We're calling set name. This is how I debug. You get the stack trace and then kind of see where we came in. These aren't useful. Then the first one that has our source code. So we can see, okay, this has to do with the testfs call. And then a lot of this is specific to testfs until we get back to our code again. So then here's mapfs. So there's a problem with this set name that we use in open. And we can go further to see where the actual panic was called. So set name is a helper because sometimes if we create a node, sometimes it's created without a name, and we have to set the name. So let's see, where was this? So mapfs, the way it works is the first thing it does is check to see if the name that we're opening is a file directly in our map. So it looks that up. And if it does find it, it does a stat on kind of the root of that file system. And if the root of that file system is not a directory, then we will just kind of call open on that. And that will open the file in that subfile system. If it's not a directory, then, or if it's not a file and it's a directory, then it kind of goes through all this other stuff here and ultimately returns a directory. Most of this being, are we trying to open a directory that's a parent path to one of the entries in here? But set name, this is kind of this little quirk in our plans, because we can create a file system that is just a file that lives at period or root of the file system. But we won't know what the name of that file is. Unless it has a name defined for it. And a lot of the time what we want is the name, the base name that we had open here. This is a hierarchical, if I can understand if this is hard to follow, like it's a hierarchical system and these nested systems are very hard to follow. So hopefully this is somewhat followable. But the problem is that we need to set the name of this file. And the way we do that is with the set name that does a type assertion that says, okay, we're working file systems, but we know most of the time we're building these with, this node type that we made. And if we type assert it to that, then we can set the name. If it's a file system that's not based on N, we can't set the name, so we panicked. So I'm not sure.
Sorry to interrupt. I just wanted to let you know it's a little bit after noon. Whenever you
halfway
feel like a break would be good. Mm-hmm.
Let me kind of figure out what this problem is, and then we'll take a break. You guys can reset the stream, and then we'll try and fix this problem.
Sounds good.
But thanks for that. Let's see. I guess, okay, so here we have a file system, but we're not defining the root. And normally the root can be defined. Actually, I don't know. I guess the root would normally be a synthesized directory. So the problem is it's not a synthesized directory. So it's not. Are we not creating synthesized directories with N? Mapfs. Yeah, we're using node to synthesize those directories. So we can just start a quick little unfortunately, because this might be a pointer, it's not going to tell us much about it. I guess we'll include the name. So we'll see the name that was opened that set name fails on. Oh boy. apparently, because it's a n and n has we created a stringer method, and this is called whenever you like print line and log print line. It's showing us almost what you'd see in a directory listing. So that's kind of funny. Instead of just a pointer ID, it gave us this representation. But at least we can see the before the failure. The last thing is when it was looking at dir. Trying to open dir. Which is an entry, but it is not an n, right? Because it's another mapfs. So this makes sense. We didn't use node to define this entry in here because it should work with mapfs or union or really anything that is a file system, except for the fact that so far we kind of assume that it's always going to be n, and so we need to figure out what to do in that case here. So anyway, we'll take a break and then we'll come back maybe 5 minutes. The fire alarm hasn't gone off. Hopefully it won't.
Fingers crossed.
But that could happen. All right, 5 minute
All right.
break.
12:19.
Okay.
See ya. Hello.
Oh, you're back?
Yep, I'm back.
Give Tara a minute.
For the stream, is it like possible for you to like while you are explaining some of like the nested functions or what's happening with the system, if you could show like a visual graph or something on the screen?
Yeah, I mean, I just need to know when that's helpful.
Okay.
Yeah. It's like some of the measures, like for example, if you're like this is explaining like the file system structure, that you can like with the graph, it might be helpful if it's like you can show the root and then there's like a file system that can have like multiple directories under
Yeah,
that.
yeah. Let's.
I'm back. I'm not sure if you heard me.
Yeah. Welcome back.
Okay.
Let's see. Well, I have an idea, but I'll have to code that up off stream. So next stream I can make a way to visualize these file systems. I think that would be really helpful. That's a good idea. We'll just have to kind of get through this one without it.
Oh yeah, yeah. It's just like basically sometimes it just helps like trying to visualize like for example like
Absolutely.
normally we use like whiteboarding
Absolutely.
basically.
Yeah, absolutely. Like it would be pretty easy to, I'm thinking of a tool that could kind of visualize or print out what this would look like as a directory tree,
Yeah.
and then this one as well. So then you can kind of visually see what it'd look like. But yeah, we'll get that for the next stream. I think I figured out what we need to do here. So in the case where mapfs, where we use a node for the entries, this set name works because it's going to look at what that see if that file system is a node, and then we can just set the name on it. And so now it'll have a name. I'm wondering, one way around this is, I mean, this is a general like mounting issue. Maybe I will try and visualize it with in our notes here, or in the to do. So if we have a directory, nope, this is going to be annoying with autocomplete. And maybe we'll go in and put a couple things in there. And then we have another directory. And it's got, I don't know, A and B. So these are two... What is the root, though? So actually the root is here on both of these. Let's do it like this. All right, so dot basically signifies that this is a file system, And I'm including dot here because for every file system, there's always a dot, the root entry file. And so if we wanted to kind of mount this file system or this directory of 2 files A and B, maybe as bar, maybe we'll say, so kind of the end result that we want looks something like this, right? We want to effectively mount this file system at this file or this directory that we've made in this file system called bar. That effectively means that this file is now called bar. But the way we've defined this file system, we didn't. So one thing that we could do is always define this file system where the root is called bar. We could do something like this, where we say this subfile system is, whatever, a string, we'll make it the name. So the problem with this, though, is now wherever we mount this, it's always going to be called bar. And the problem is we might have another directory. The whole point of making this a file, this little modular file system, is maybe we'll make another file system, and over here we want to mount it as baz, right? So we have this problem where we have this file system and we can't hard code the name for the root with it. It's really dependent on where we mounted it, what file system it's on. And so that's effectively what I was trying to do with set name, is assuming you're making these file systems with just rn, our little node constructor, we can use set name to set the name for that root. But because these aren't designed for working with just n, it could be any file system, we're not always going to have the opportunity to set the name on it. And so in this case, where we have where we're taking a mapfs and putting it under an entry in another mapfs, mapfs is not a node, so it can't set name on it. And that's why we're getting this failure. But basically it's an insufficient way to deal with this problem, is when you're creating a file system, or composing these file systems, we need some way to change the name of the root when accessed from this context, which will be different than if we access it from this file system over here where we mounted it as baz. So I have this idea, which is we could basically create a wrapper for file systems. So it might look something like, we'll do this down here. We'll not export it yet, but we'll say named fs. And it is a file system. I'm trying to think structurally. We'll do it as a struct first. and then embed. Thanks, autocomplete. Sometimes autocomplete almost feels like it's more confusing than not having autocomplete. But roughly the idea is, we can kind of wrap a file system in a new type. Because it's embedding file system, it basically passes through all the methods and the properties. And then we have we're basically adding a field to it called name, which, I don't know, we'll set somehow, but then we implement open on this type. In a way where we check if this is almost correct. So basically, if it's not the root, we'll just kind of pass this along to the file system that we've embedded. But if we're trying to open root, we can return a file that has the name that we used here. But ideally, we actually want to return whatever entry this file system would return and then change the name on it. So we would actually want to try to do maybe let's see, how would we do this? Try and do a stat on the inner file system, which will give us file info about the file. And then we can override the name. We'll have to create kind of another wrapper, I think. Open stat. Basically a named file. I don't know why it's not. It should know that we're talking about a file. Let's see, ultimately we do have to return a file, but we want that file's stat to return a different name. There might be a simpler way to do this, but let's see. So we'll call stat on the inner file to have that. And then let's see if this is almost correct. So named file wraps a file and it overwrites its stat, which returns file info. Then we call stat on the inner file to get its file info. And we more or less want to return that file info object, but with the name replaced. And I actually made it so that you could pass a file info into Node, and it will set all of the attributes to whatever file info is set, and then we could set a different name. So this should effectively given we have a file, and we probably should write a test for this. Will kind of help us understand it a little better too. So first we'll kind of just test named file. So first we need a file of some kind, which we can use and to create. So we'll create a file called foo, and then if we do bytes, yep. So this will basically create a file that has a name and data, and then we're going to create a wrapper using, no, it keeps, I want to test named file first. We'll get to FS. Stop doing FS. This is the first time I've kind of really struggled with this stupid autocomplete thing. But we want to name it bar. Oh, here's the other thing: is an entry is not specifically a file. If we need an actual FS file, because we have to do a open dot to get it. Node doesn't implement the file interface directly, but it returns something when you call open. So now we have a file that looks like this. We wrap it in named file. And yeah, it looks like this. Almost got it. Sure. So we're testing to see if we call stat on this named file that we've renamed, will its name be bar or will it be foo? It should be bar, so let's run this test. I think there's a way. Let's try using the editors. Testing. Declared and not used. We're going to come back to this. All right. So that passes. So we've made a little wrapper that will rename a file effectively. So that's part of the problem, part of the solution rather. Now we need to wrap a file system that I guess maybe instead of a stat we do an open. So we would open it specifically the root, and this is supposed to be file F, and this will be whatever our name is. So effectively it's using our named file wrapper to create a wrapper for a file system that will, for the most part, hand open off to the file system, except for the case where we open the root file. In that case, we then open the root file of the inner file system and then wrap it with our named file, specifying the new name. That follow? We can write a test for that. Let's see. So first we'll create a file system, maybe a mapfs. So this is like creating a directory where we have a file, foo. Maybe we'll call this the inner file system, and then this will be the outer file system. Or no, we aren't testing that. We're just testing the fact that let's see, renamed fsys. So I guess what we could do, if we let's first see what the name is for this file system. If we did an fstat on the root directory, what do we get for the name? All right, run it. We get dot. And what we're trying to do is rename dot to something else. So maybe we'll create a test case to make sure that, like, before we've renamed it, we do expect the name to just be dot. Yeah, name is not set to as expected by default. Then we'll create the wrapper. And then we're going to do stat again. And we'll print the name for now just to see what it does. Cannot use renamed. Oh, this needs to be a pointer. Okay, so printed out bar. So it looks like we effectively renamed the root of this file system. I'll create now an actual test. All right, so we've made this little utility. We just need to somehow make it more usable. We're not exporting these types, so maybe we can create a function called rename. Let's see. Maybe we'll call it named file system. Maybe it works like that. So now whenever we want to rename the root of a file system, we'll call named file system, give it a name, and it will wrap it like this. We could even just update our test real quick to be like that, so that is a little nicer. Okay, these tests pass. So now let's go back to where we call set name. So I guess we don't actually want to set the name. We just want to wrap the name, if that makes sense. Create a new file system that has a name And our new named file system should work with any file system, regardless if it's somehow built with our node or not. So maybe we won't use set name here. After all, we can just do kind of set sub fs to that. Name here might be, we actually want the base name of the path. So if, if we were opening a file called, foo bar baz, we would want the name of the file system here to be baz. So path base gives us the base of this path. This might be all we need to do. Well, we got rid of set name. So I guess this test might work. This was the one that was failing, that we got that panic. All right, so we're not there yet. It seems like it found dir, but for whatever reason, it's not finding these subfiles. Why is that? Oh, I know why. Because the whole point of this was to implement the code that allows this. The way mapfs works, you can see initially it will check to see if the name we're looking up is in its map. And then otherwise, it's assuming that the name you're looking up might need to be synthesized because it could be a parent, something like Fortune, where we don't have an entry in the map, but we need to synthesize. If you were to open Fortune or Fortune K, we would need to create directories for those. And that's pretty much what all of this code does. Quite a lot to do that. If for some reason, and in that process, it can determine, okay, there might be a case where what you're looking up is not any apparent path to any of the entries, and so it says it doesn't exist. But we also have another case here because it's possible that we could open a file specifically in here or a file that is a parent path, but there's also the case where maybe we're trying to open a subpath of one of these file systems. Like, basically we want dir hello. Dir hello is not in here, and it's not a case where we're trying to synthesize a parent. We actually want to look into our, whatever file system is here. So we need to look at the try to open a file within this found file system. If that's the, so we need to, I guess, first let's see, basically iterate over all of our file systems and see if, I guess we want we'll do P for path, because path is a package name, so trying to avoid using path as a variable name. But yeah, it looks like we're trying to see, does name have this path as a prefix? This isn't right. Come on, autocomplete. We want to check if, I don't know why it's getting that wrong. We want to check to see if the name that we're trying to open, as an example, I'll put one of our test cases here, dir hello. And we have an entry, a file system at dir. So P, let's see. And I guess we might also want to check P with a slash. So we're checking to see, we're trying to open dir hello. We have a dir entry. So we're detecting this case. And if that's the case, oh God, what is it auto-completing for us? I don't know if this has anything to do with what we want to do. We want to trim. So now we want to get this part so we can open that on the file system. So maybe we'll call this like a relative path where we trim the prefix off. It's using namedfs, which we probably want to do, but then I don't know about this other part. Because this is open, we basically just want to open it. Or no, maybe we want to check to see if it exists. But not dot. We want to check to see if this relative path. Actually, no, we'll just do an open like that. And if it doesn't exist, then we'll get the error from that file system. But yeah, I think this is all we need to do to support, mapfs being able to open paths that go into these file systems. It might be just that simple. Let's try our test. No. Well, that's a bummer. I guess we'll check this out if we're in here. Just see if we get that. It's not even getting that. Why not? Name and I guess it's possible. Well, we'll see. Okay. So I guess what we're seeing are all the names that it was trying to open. Mostly it's trying to open dot and dir. It's saying, it's as if it's not even trying to open dir hello. Let's just do that so we can see what it's trying to open. And it is kind of nested, so we're going to see a lot of these. But I don't even see okay, open dir. And we can see that then it doesn't open. I'm a little confused now. I don't see it even trying to do an open on anything other than... This is starting to get confusing. So you were telling it, hey, we want these files, so it should be trying to open those files on M, but it looks like we never even really get that. But I'm wondering if that's because somehow directory is not showing up as a directory or something. I don't know if we actually want to see how this is implemented. It's going through, I don't know what testfs does. Check dir, check open. Maybe it's effectively walking it, and so somehow is dir not showing up as a directory. If we open dir, we get OK. Subfs, we rename it. We stat the root of it. If it's a file, we just open it directly. But if it's a directory, then we'll keep going. And so that's where we should hit this. Man, the music stopped, which means we're about out of time.
Yeah, almost one.
It's really nice when coding kind of just comes together, but most of the time it doesn't. We have to deal with systems that don't quite work. And that's where the unpredictability is. Who knows how long it'll take to fix this? So I guess we'll just have to stop here. Luckily, that means that I'll probably figure this out off stream. And then next stream, we can kind of move on to, we'll have mapfs. And once that works, we kind of have everything we need, except we probably want to port the mapfs that we made and put it in fskit, because we don't need a lot of this. We can kind of simplify its implementation by using, our node and stuff like that. And once we get that out of the way, which will be pretty quick, we can then finally put this together.
Exciting.
Yeah. I originally thought we would get to doing this file system in the first stream, like 3 streams ago, but that's how programming works. Was this helpful, Rohit? The kind of visualizing?
Oh yeah,
In
that
text.
visualization helped a lot.
Okay, great. And it's great to have you on stream asking for that so that people that are watching, you sort of stand in for them.
Yeah. Yeah, that visualization kind of like made it clear what we are trying to do. Then I could follow up with the code.
Yes.
Okay, that's what. Then I can visualize while coding that. Okay, yeah, that's what we are trying to achieve, and we can do it.
Yeah. So I'll keep that in mind. I can do those kinds of things going forward. But yep. For more Wanix development, I guess we'll be back same time on Wednesday. So thanks for hanging out with us today. Let's see. You guys can take off. I'm going to raid the Old Timey Computer Show because that's what I do.
Thank you.
All right. Rohit, Tara, thank you. And we'll be back on Wednesday.
See ya.
But who likes it?